Section 6.3, Day 2, Vectors in the Plane. We're going to write vectors as linear combinations of unit vectors and also perform some basic operations. So example 1, we're just going to perform some basic operation of vectors. Given vector v is 2, 3 and w is 5, negative 4, we're going to add vector v plus vector w. Now we did this the other video, but we did it graphically. Now we're going to do it algebraically. So to add two vectors together, we just add their components 2 and 5 and 3 and negative 4. So we would add 2 plus 5 and 3 and negative 4. So that would give us v plus w would be 7, negative 1. And that's it. That's how you add two vectors. Now on B, we have scalar and subtraction or addition of a negative 2w. So this would look like 3 times vector v minus 2 times vector w. And so the scalar just multiplies the component. So 3 and 2 would give you 6. 3 and 3 is 9. Plus, and then I'll do negative 2, and 5 is negative 10, and negative 2 and negative 4 is 8. And then we can add those two up, and then that will give us 6 plus negative 10 is negative 4, and 9 and 8 is 17. So 3 times vector v minus 2 times vector w would be negative 4, 17. Alright, let's look at C. C is a magnitude of the sum of the two vectors. So that would be v plus w, which means we're looking for the magnitude of 7, negative 1 as a vector. So that would be the square root of 7 squared plus negative 1 squared. So we have 49 plus 1, and that would be the square root of 50, which simplifies to 5 square roots of 2. Alright, what about D? Now D looks similar to C, but we're looking for the vector v, the magnitude of vector v plus the magnitude of vector w. So we split them apart. Will those two quantities be the same? Well, vector v's magnitude would be 2 squared plus 3 squared, and vector w would be 5 squared plus negative 4 squared. So let's see what we get. We get the square root of 4 plus 9, which would be the square root of 13, plus the square root of 25, plus 16, which would be the square root of 41. So the square root of 13 plus the square root of 41. Can't simplify either one of those. So is part C equivalent to part D? And the answer to that is clearly no. So you cannot break up two vectors and find their magnitude and it be the same as the sum of the two vectors' magnitude. So there are some basic operations of vectors. Next is a unit vector. So when we find the unit of something, it has a magnitude of 1. Alright, so the scalar multiplier of v, but it's in the same direction as v. So if you look, the unit vector u is equal to the vector v, so this is the vector, divided by its length or its magnitude. Another way you can write that is to do 1 divided by its magnitude times the vector v. Alright, they're the same thing. So let's take a look at an example of this. So find the unit vector in the direction of v equals 3, negative 2. So we want to find the unit vector. So once again, the unit vector, it has the same direction, but the magnitude would be 1. So the unit vector is equal to the vector divided by its magnitude. So this would be 3, negative 2 divided by the magnitude. So what's the magnitude of vector v? That's equal to the square root of 3 squared plus negative 2 squared. 9 plus 4, so that would be equal to the square root of 13. So this would be divided by the square root of 13. So what does that give us? Well, we're going to take And I'm going to rewrite this the other way because I think it makes a little bit more sense. So it's 1 divided by the magnitude times vector v, which is 3, negative 2. So you actually are able to see that this represents a scalar multiplication. So that's a value times the actual vector. So what is that equivalent to? Well, that'll be equal to 1 divided by the square root of 3 times 3. So that would be 3 over the square root of 13, comma, negative 2 over the square root of 13. And so when we rationalize the denominator, that will give us 3 square root of 13 over 13 and negative 2 square root of 13 over 13. So that's equal to the unit vector. So same direction, but now the magnitude is 1. So now in part B, we're going to verify that the magnitude actually is 1. So we're going to find the magnitude of the unit vector, which should equal 1. So we will do the distance formula. So 3 square root of 13 over 3, or over 13, sorry, squared, plus negative 2 square root of 13 over 13 squared. So if we square that, we will get 3 squared, which is 9, and then the square root of 13 squared would be times 13, and then the denominator is also squared, which is 169, or 13 squared. So we'll actually be able to cancel out that 13, plus negative 2 squared is 4, square root of 13 squared is 13, and then once again the denominator is also squared, which would be 169. But the reason I didn't do that is because now I can actually cancel and see that this 13 will cancel with one of those. So that'll leave us with 9/13 plus this 13 will cancel with one of those, and that will be 4/13, which is equal to the square root of 9 plus 14 is 13 over 13. So the square root of 1 is 1. So therefore, because the unit vector has a magnitude of 1, it verifies that what we have in part A would be correct. Example 3. Find the vector v with the given magnitude, which is given as 3, and in the same direction as u. U is equal to 4, comma, negative 4. So we're trying to find vector v with a magnitude of 3, but in the same direction as u. So just think about what that means and what are we trying to accomplish here? What are we trying to kind of do? So once again, as you're thinking about this, the magnitude of vector v is 3, and a different vector u is at 4, comma, negative 4. And what we want is we want vector v with the given magnitude of 3, but we want it in the same direction as u. So what we need to do is take vector u and find its unit vector. And what is this going to do? Well, if we find its unit vector, then that will take its magnitude down to 1. So it'll still have the same direction, but it'll have a magnitude of 1. And if we have the magnitude of the unit vector is equal to 1, then we know the direction, and then we just need to multiply it by 3 because we know the magnitude of vector v is 3. All right, so let's go about kind of doing that process there. So we want to find the magnitude of u first, okay? So we don't know that it's equal to 1, so I'm going to erase this. I don't want you to get confused, but we don't know it's equal to 1. We're going to find its unit vector, but since its vector is u as well, we want to be careful here. So the magnitude of vector u would be 4 squared plus negative 4 squared. So 16 plus 16 is 32. And then the square root of 32 is equal to 4 square roots of 2. So this isn't the unit vector, this is just vector u. So vector u's magnitude is 4 square roots of 2. So to find the unit vector, and I want to write this out because I want to make sure I'm clear here. So to find the unit vector of vector u, so the unit vector of vector u, so this would be the unit vector. This would be equal to vector u, which would be 4, negative 4, over its magnitude, 4 square roots of 2. So that'd be 4 over 4 square roots of 2. The 4's would cancel and give you 1 over the square root of 2. And negative 4 over 4 square roots of 2 would give you negative 1 over the square root of 2. And then we can simplify that to square root of 2 over 2 and negative square root of 2 over 2. So this is the unit vector of u. Okay, so unit vector of u. Alright, so now that we have the unit vector, and we know that the magnitude of vector v is 3, then to find vector v in the same direction of u, we can just take 3 times the unit vector, which was square root of 2 over 2 and negative square root of 2 over 2, and that will give us vector v as 3 square roots of 2 over 2 and negative 3 square roots of 2 over 2. So to kind of show you this graphically as to what we just did is we took the unit vector u at 4, negative 4, so it'd be from here to here, okay, and we created vector v in the same direction but with a magnitude of 3. So the magnitude of the original was 4 square roots of 2, so the vector v would be a little bit shorter than that, but in the same direction. Alright, linear combination of unit vectors. So vector I, 1, 0, would be kind of our horizontal distance, so we're going 1 unit to the right. We're not going up or down, that's why the y value there is 0. And then j is 0, 1. So we didn't move left or right, but we moved up 1 unit. So those are still vectors. They're unit vectors of 1 unit. And v is equal to v sub 1, v sub 2. That is your component form. Okay? And so we can rewrite this as v is equal to v sub 1 times I, or 1, 0, plus v sub 2 times j, or 0, 1. V sub 1 and v sub 2 just represent your components, all right, those scalars. And so if we do that, then 1, 0 is the same thing as I from above, and 0, 1 is the same thing as j, your standard unit vectors. So we can rewrite a vector v from component form to linear combination form, which is v sub 1i plus v sub 2j. So for example, if we had v is equal to 2, 3 in component form, it's the same thing if we write it as 2i plus 3j. So those two are equivalent, they're just different forms. The first one is component form and the second one is linear combination form. So once again, the first one's component form and the second one is linear combination. And so now we'll look at some more vector operations, but we will be looking at these in linear combination form. So example 4, 3v minus 2w, but instead of once again giving you 2, negative 3, we're going to do v is equal to 2i minus 3j. So just same thing, just a different way to write these so you see the different forms. So this would be 3 times vector v, which would be 2i minus 3j, minus 2 times vector w, 5i minus j. And so really we're doing the same thing we did before. We're going to multiply the scalar, so it would be 6i minus 9j minus 10i plus 2j. And now we can combine the I vector and the j vector. So you get 6i minus 10i would be negative 4i, and negative 9j plus 2j is negative 7j. So this is equal to 3 times vector v minus 2 times vector w. Negative 4i minus 7j is in linear combination form. Once again, component form, it would look like this. So once again, go ahead and write the summary. We learned a little bit more about vectors today, especially the unit vector. Also being able to write vectors in the linear combination form as well when we did some different operations with both of those.